At the very tip of Africa lies iThemba Laboratory for accelerator-based science, the largest accelerator facility in the Southern Hemisphere and the only cyclotron facility on the African continent. iThemba Labs offers unique research capabilities to local and international researchers. The Cape Town facility also produces radiopharmaceuticals for the diagnosis and treatment of cancer. iThemba Labs is where science comes to life, where real people are using science in various ways to impact the lives of every South African. Visit their Facebook page, iThemba Labs Cape, or email director@tlabs.ac.za. And we are with iThemba Labs right here in the studio at Helderberg FM 93.6. Welcome, Dr. Gillian, once again, and welcome, Dr. Muneer Sakildien. Sakildien
sounds good.
Baie welkom. How are you guys doing?
All good my side. Thanks for having us.
Thank you very much, Johan. I'm also very good.
Fantastic. I'm always very excited to have this chat with you guys. You've had a busy week down there at the CTICC with a science, well, I almost said science fair, but it's more like it's a nuclear physicist convention. Is that right? Or is it more like a nuclear physics convention? Is that even the same thing?
Yeah, it is called the International Nuclear Physics Conference. So
yes.
It's the biggest conference, first time in Africa, first time in South Africa. And it's basically a place where, specialists, scholars in nuclear physics, hadron physics, particle physics come together to share, new research, new findings, new developments.
And right before we go to the rest of the program, I am so interested to hear a little bit more about that. Was there anything specific that was happening or that was mentioned at this conference that kind of blew your minds that you would like to share with us? Anything exciting?
Well, I think for me the most exciting was the public lecture that was given by Jordi Jose. And it was just this, fascinating journey in terms of who we are, where we come from, and what we're made of. So the fact that we're made of stuff, we call the stuff matter. Matter is made of molecules. Molecules made up of atoms. Atoms contain, nucleons, or the nucleus, nucleons, electrons, substructure. But at the end of the day, the air that I breathe, some of it I use, the rest I exhale. And after a while, you will inhale that same air. And everything gets recycled. So at the end of the day, we are more alike than what we might want to admit.
We are one.
There we go.
And it's true that every 7 years our cells create, basically we're a new person, right? Something like that. Is that true?
We shed some skin and we continue. Yeah.
Okay, well, if I'm as smart as you are in 7 years, I'll be very happy, Dr. Gillian. But talking about smart, we've got someone else in the house here. We've got Dr. Muneer in the house. And iThemba Labs, advancing knowledge, transforming lives, inspiring a nation. The research and development done at iThemba Labs relies on the availability of beams, of accelerated particles. But who are, apart from the research scientists, all the other superheroes working behind the scenes? Muneer, how are you? Today I want to wrap my head around the process involved at iThemba Labs. How exactly do you produce a beam of particles? Let's take protons as an example.
Good morning, Johan, and thank you very much. Or shall I say good afternoon? Thank you very much for hosting us today. So with regards to your question, protons is produced by injecting hydrogen. So typically one takes a hydrogen gas and one injects this hydrogen gas into something that we call an ion source. So an ion source, as the name implies, is a device that takes the gas, and the gas removes the electrons from the gas and creates generally a charged particle. In this case, if you remove the electron, you create a positively charged particle, i.e. a proton. So if one injects a gas of hydrogen into this ion source, and hydrogen, as most of the audience might know, hydrogen consists of a proton and an electron. So when one removes the electron, one in essence creates an ion, a charged particle, a proton in this particular case. So this proton, one can then, because it has got a net positive charge, one can then start manipulating the trajectory, i.e. the movement of the particle using electric and magnetic fields. So the way one creates a beam of particles, in essence what a beam of particles or a beam of protons is just a number of particles that all move together. So the first step in this whole production of a beam of particles is to take a hydrogen gas, expose the hydrogen gas to a number of heated electrons. When this number of heated electrons has an interaction with the with the molecules or with the atoms of the gas. One removes one of the bound electrons, and in so doing, one creates a positively charged particle, i.e. a proton, and all these protons are then extracted from this device called the ion source. And in so doing, one then has what we typically in the world of accelerator physics call a beam of particles.
That is phenomenal, and I'm gonna act like I understand everything you say. But that is really, it sounds, it's just always fascinating to me how this is happening right over here in the Western Cape, because we tend to think that these things only happen, in these bigger first world countries with their big hadron collider places and all those. Yet there's so much happening at iThemba Labs. Okay, so you are heading up the accelerator operations division, but what is an accelerator, and how many do you have at iThemba Labs?
Okay, so thank you very much for the question. Just to tie up to what I just earlier explained. So when you have a beam of charged particles, i.e. protons in this particular case, one typically wants to use these accelerated particles for all sorts of applications. And as you might, as the audience might or might not know, at iThemba Labs, we predominantly have two, or in the past, three large areas of applications. So this is isotope radionuclide production, and for fundamental nuclear physics research. And in years gone by, we also did all sorts of therapies. So, and by this I mean proton and neutron therapy. So coming back to your question, so these charged particles then has to be accelerated, and the device that one used to accelerate these charged particles is a device called an accelerator. So basically one gets a number of different types of accelerators. You either get an accelerator that accelerates the particles with a so-called DC field, so with a electric field that does not change as a function of time, or you can accelerate the charged particles with a AC field, i.e. a electric field that changes as a function of time. So the specific type of accelerator that we have at iThemba Labs, actually we've got a number of different types. So we have, at this stage, we have three circular accelerators. So these are accelerators that use an AC field to accelerate the charged particles. And then one also have a DC accelerator. So an accelerator that uses a constant electric field to accelerate the charged particles. So when you have this charged particle that you've created inside your ion source, so as we explained earlier, if you have a proton and you expose this proton to a electric field, so one can think of an electric field. If you think of two plates, the one plate is positively charged and the other plate is negatively charged. So when one puts a positively charged particle, in this case a proton, between the two plates, the one plate will push the particle away, whereas the other plate will attract the particle. And in so doing, the particle gets a net energy increase, so the kinetic energy of the particle increases during such an interaction. And this is, in essence, what happens inside a cyclotron. So the cyclotron, firstly, you create the charged particle inside the ion source, then you confine the charged particle using very, very strong magnetic fields. And thirdly, you expose these charged particles to an alternating electric field in our resonance cyclotron, and in so doing you give the particle an energy kick. And if one does the fundamental or the calculations, one can typically show that such a particle can typically go around the Earth, depending of course on its kinetic energy, typically can go around the Earth maybe 9 times around the Earth in 1 second. So it is really a particle that moves extremely fast. So in short, an accelerator is a device that takes a charged particle, accelerates the charged particle from some thermal kinetic energy up to the required energy. And in our case, the required energy is typically in the region of mega electron volt. So mega meaning 10 to the power 6, so million electron volt. And an electron volt is one. So if you take a fundamental particle and you accelerate it again over a potential difference of 1 volt, you give this particle an energy, a kinetic energy of 1 electron volt. So what we do is we accelerate charged particles to typically the order of 200 mega electron volts, a proton, I mean.
And there you have it, Super Science 101. Can't believe it. Thank you very much for that masterclass. But now let's talk about the dangers of this thing. You know, even when you think of an accelerator or a collider, you think of things exploding and things possibly, going wrong. What set of challenges do you have to work with? And has there ever been an incident where, maybe someone turned into some mutant monster or something?
Nothing like that as far as I know. Perhaps Dr. Arlenson knows something different.
We will probably not know that because otherwise the sponsors, nobody's allowed to know that.
I wasn't born this way.
In any case, coming back to your question, thank you very much. Actually, a very good question. So one must bear in mind, as Dr. Arlenson also reminded me earlier in this week, that these particles that one are talking about are extremely, extremely small. So it's of course not possible to see them with the naked eye. So what then one typically does is one uses all sorts of fancy equipment that we call diagnostics to view the particles. And the trajectory of the particles, as I mentioned earlier, is manipulated using these electric and magnetic fields. So one can think of, if you take these particles and you accelerate it. So if one takes a particle and one accelerates it to typically the energies that I mentioned, this mega electron volt, these particles have a huge number or a huge amount of energy. So and as I tried to, or I was alluding to earlier, it's not typically one particle, but it's billions and billions of particles. It's definitely orders of magnitude of particles more than what we have people on this planet. So if one takes all of these particles and one stops all of these particles, and one must also bear in mind that these particles occupy a very, very small space in space, a small area or small volume in space. So if one takes all of these particles and one stop it on any surface, you typically deposit all of this energy of all of these particles on the small area. And unfortunately, in the past, due to a number of different reasons, one has had these types of accidents happen. So typically all of the particles would then interact with the containment vessel, and in so doing one burns a hole in the vessel. And this is typically one of the worst types of problems that we've had. The result, of course, is that we lose so-called vacuum. So all of the particles is moving in a space that is where all the residual gas molecules has been pumped out, i.e. a vacuum. And then you have the air rushing in from the ambient space into this area or into this containment vessel, and in so doing you stop the whole process of acceleration of charged particles. So typically these are some of the worst accidents that has happened, and there's quite a number of reasons why this type of thing could happen.
That is phenomenal. So it's always so weird to think of these big machines to conduct this, I almost want to say, little experiment. Like you need these big tools and things to do something so microscopically significant, yet in the greater scale of things it's actually such a big thing happening. And in a way, you're playing a creator of sorts. In a way, you're experimenting with things. Do you guys think you'll ever have a home kit? They will in the far future. Do you think there will be a safe way to conduct these experiments ever in the future?
Dr. Gillian, can you please assist me on this one?
Well, I don't know. I think you alluded to the fact that, when you do these experiments, you want to see small stuff. And unfortunately, what you see is related to what we call the wavelength, right? So the wavelength that you use to see determines what you see. But in terms of particles and the movement of particles, your wavelength is inversely proportional to your momentum. So the smaller the wavelength you want, the faster the particle needs to move. And in order for the particle to move faster, you need bigger and bigger and bigger machines. So iThemba's got a cyclotron, but for instance, if you go to CERN, they've got a synchrotron. And their accelerator ring, if I have it correct, fits into 22 kilometer circumference. So that so they need a big space, a big machine to be in order to make things go very fast. Of course, they accelerate, I think, up to about 99.9% the speed of light. We are probably at the 56% level.
Correct.
So if you upscale in energy, then you also upscale in size. So I think it will become probably unlikely for you to be able to do these kind of things at home. Obviously, you can do other kind of experiments with microscopes.
It's like needing 6 rugby fields for 4 Cheslin Colbys.
More or less. And you will sidestep, and you might even miss him and not know that he's there.
Our time is up, and it's always been so fun. It's never enough speaking to iThemba Labs. Thank you so much. And I'm just inviting everyone out there to go check out iThemba Labs' website, tlabs.ac.za, or drop them an email at cise@tlabs.ac.za. They have a lot of educational things, and you are allowed to visit at some point. When is visiting hours at iThemba Labs? Is there such a thing?
Well, I think at the moment it's people can reach out to me. We'll see how we can accommodate them best.
Okay.
It's obviously just understanding that we are a space that works with radiation. Radiation safety is one of the things that we are very proud of and protective of.
Dr. Gillian, Dr. Muneer, have a beautiful day. Thank you for being here.
Thank you very much, Jan.
At the very tip of Africa lies iThemba Laboratory for accelerator-based science, the largest accelerator facility in the Southern Hemisphere and the only cyclotron facility on the African continent. iThemba Labs offers unique research capabilities to local and international researchers. The Cape Town facility also produces radiopharmaceuticals for the diagnosis and treatment of cancer. iThemba Labs is where science comes to life, where real people are using science in various ways to impact the lives of every South African. Visit their Facebook page, iThemba Labs Cape, or email director@tlabs.ac.za.